Assistant Professor in LG Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Analog and Digital Communication System. So in the last video, we learned about the method for generating the FM. That was the direct method. In that, we learn about the basic fat reactance modulator and the varactor diode. In the basic fat reactance modulator, by varying the L and C component, we are able to vary the frequency and we may generate the FM wave. In case of the varactor diode, by varying the junctional capacitors, we may vary the oscillator frequency and we may generate the frequency modulated wave. So, what is the frequency modulation? It is a type of the analog angle modulation in which the instantaneous frequency FIT is linearly proportional to the instantaneous magnitude of message signal. So, the relationship between the FM and the PM is, the PM wave we can describe by writing the equation that is ST is equal to EC cos 2 pi FCT plus KP into XT, where KP is the phase sensitivity. By varying the amplitude of the modulating signal, we may vary the phase of the wave. Okay. Similarly, the FM wave, it is ST is equal to EC cos 2 pi FCT plus 2 pi KF integration 0 to t xt into dt. So, KF is the frequency sensitivity. By varying the amplitude of the modulating signal, we are able to vary the frequency of the wave. So, this way, this is the relation between the FM and the PM. As we know that, in case of the direct FM method, we were getting the frequency was not stable. So, that is why we may not use the direct FM method in case of the broadcasting. So, that is why our requirement to get the frequency stable, we may use the crystal oscillator for generating the constant as well as the stable frequency. Again, the thing is that with the crystal frequency also crystal oscillator, that by if the frequency greater than 1 megahertz, again the crystal oscillator is not producing the stable frequency. But right now we are not putting a stress onto that particular part and we are considering to select the crystal oscillator for generating the constant frequency. Okay, so the generation of the FPM using the FM. We have the modulating signal, that's XT. You may apply it to the differentiator. Output of that is this. That is the integration of v by dt of XT. You may apply that to the frequency modulator. The other input for the frequency modulator is crystal oscillator, whose equation is EC cos 2 pi FC into t, and it may produce the output that is the PM waves. So, the indirect FM, there are the two types of the method. That is, okay, here it's the output of the frequency modulator is ST is equal to EC cos 2 pi FCT plus 2 pi KF integration d by dt xt. So, integration d by dt, okay, so that will cancel and only the KF into xt. Okay, so it is EC cos 2 pi FCT plus 2 pi kf into xt. So it is EC cos 2 pi fct plus kp into xt. So by varying the amplitude of the modulating signal, we may change the phase of the particular signal. So where the kp is equal to 2 pi into kf, where kf is the frequency sensitivity. So we learn about the direct generation of the FM in the last video. It was the two types, direct method, indirect method. In the direct method, we learn the two method, reactance modulator and the Variactor diode modulator. Now in this video, we will learn about the other method of generating the FM. It's a Armstrong method. Now what is the difference between the indirect FM and the direct FM? In the indirect FM, we are not generating the FM directly, but by the use of the phase modulated output, the PM output, we will generate the FM wave. So that is why we are generating indirectly the FM waves using the PM. And the advantage of using this method, that is to have the stable frequency and the effect of the noise, that is also less. So in the direct FM, we were using the LC tank circuit. So we have the reactive parameters like the L and C. So by the use of this reactive parameter, we may have the change in the frequency. But that change in the frequency, but output, it's not stable. So that is why it may not use for the communication broadcasting purpose. As we know that when we listen the radio Mirchi output, that is at the 98.3. Now if the frequency is not stable, we may not listen the output, we may not get the output particularly at the 98.3. So frequency that can be varied, and according to that you need to tune. So that is why every time in the communication broadcasting, we need a constant frequency or the stable frequency. So that is why here we can see, you can see the diagram, that is for the phase modulator and the frequency modulator. Now here you can see that my empty modulating signal is applied to the phase modulator. The output of the phase modulator is AC cos omega ct plus kp into mt, where kp is phase sensitivity. And this is my frequency modulator. Input for the frequency modulator is empty, and the output of the frequency modulator is AC cos omega ct plus kf into mt into dt. Now we have wanted the stable frequency, so we have to use the indirect method for generating the FM. So I will use this particular block diagram, but I need to generate the FM wave. So I need to modify this equation, and I need to generate the FM wave which would be like this. So what we can do? So now the modification in this block diagram, so it is that now I will not apply empty signal directly to the PM, but now I want the integrated output. So now you can see over here there is an integrator and empty input is given to the integrator. So output of the integrator is integration of empty. So that integrated modulating signal is given to the phase modulator. So what is the output of the phase modulator now? It's a AC cos omega ct plus kp integration m of t. Now you can see that this output that is similar to this. So we can say that this is the block diagram for generating the FM wave using the phase modulator. So using the PM output, we are generating the FM, and that is known as the indirect method for generating the FM. So the method which is used for getting the stable frequency, it's a Armstrong method of FM generation. So it's the indirect method because the modulating signal directly varies the phase of the carrier and which indirectly changes the frequency. So you may also say that the modulating signal amplitude, while it changes, there is a change in the phase. So mt is proportional to the phi t. Now I need to remove my proportionality constant. So I will put here that the replace proportionality constant by the kp. So mt is equal to kp into phi t. So as there is a phase sensitivity, okay, that can be changed. There is a change in the phase, okay, we will get. So this is the block diagram of Armstrong method of FM generation. Now here the diagram which I discussed earlier about the indirect FM. So here you can see that we have the phase modulator. We have the one, you can see that the dotted part that is shown in the diagram, it's a phase modulator. And the phase modulator output is given to the multipliers and the amplifiers. And here you can see that the modulating signal which is applied. Okay, so now we will first of all discuss about the phase modulator. Here you can see that we use the crystal oscillator. So now we use the crystal oscillator. The crystal oscillator will generate the constant frequency. So constant unmodulated carrier which will be generated by the crystal. The output of the crystal oscillator is given to the buffer. So whatever the signal level is there, that can be passed exactly through the buffer, and the carrier output is given to the 90-degree phase shifter. So my unmodulated carrier, now it will be 90-degree phase shifted. So 90-degree phase shifted carrier output is given to the balance modulator. Now the balance modulator gives me the output that are the two sideband and the suppressed carrier. So now output of the balance modulator, that are only sidebands, that are the upper sideband and the lower sideband, which is given to the combining network. So in the combining network, the two sideband and the one carrier will come, and that will gives me the output, which is my FM wave. Here you can see that while the modulating signal which is also applied, then it provides me the equalized modulating signal output, and it can be also added with the balance modulator output. So according to the amplitude of the modulating signal, this sideband amplitude that can be also varied, and according to that the frequency, the phase that can be varied for this particular FM wave. So now this FM wave, its output is the narrowband FM. Narrowband FM whose modulation index is less than 1 and which have the lower frequency. So now to generate the high frequency, we need to pass it from the group of the multipliers. So n number of the multipliers are there by which my FM wave low frequency is multiplied, and we are able to generate the high frequency wave. So that group of the multiplier output, that's a high frequency WBFM wave, wide band frequency modulated wave. It is given to the mixer. Mixer will just change the center frequency, and again it is passed through the group of the multipliers, and through the class C power amplifier it is transmitted via the transmitting antennas. Now the things can be more clear if we learn about the phasor diagram of this particular method. So one by one we will study the phase diagram of the Armstrong method. So the first is unmodulated carrier. It is passed through the 90-degree phase shifter. So you can see that the 90-degree phase shifted output. It is passed through the balance modulator. Balance modulator output is two sideband. So you have the VUSB and the VLSB. The resultant vector of the VUSB and the VLSB is what? It's a VM. So now this way the resultant of the sideband we get. It is passed through the, so now the balance modulator output and the carrier signal given to the combining network. So here in the last diagram you can see that the VUSB, VLSB, the resultant output is VM and the unmodulated carrier VC. So the resultant signal is what? It's a narrow band FM. So this way the output we can generate. So you can see that the source of the carrier for the Armstrong transmitter, it's a carrier oscillator. A relatively low frequency subcarrier is phase shifted by 90 degree and it is fed to the balance modulator and mixed with the modulating signal. DSB output, that is what? The two sideband suppressed carrier. So it is the unmodulated carrier. Then after it is 90 degree phase shifted carrier. Then it is the balance modulator output. The resultant sidebands you can see. Okay, that mixed with the unmodulated carrier, and you can see that the resultant at the output of the combining network, that is nothing but the narrow band FM wave. So it is seen that the output from the combining network is a signal whose phase is varied by FM and the magnitude is directly proportional to the magnitude of the VM. So the modulation index at the output of the combining network is inadequate to produce a WBFM and therefore must be multiplied and amplified before the transmitting, and we can generate the desired output using this. So narrowband FM with a small frequency deviation is transformed into the wideband FM with the large frequency deviation. So this way we are generating the stable frequency using the Armstrong method. And since the crystal oscillator that is used for generating the constant frequency, the stable frequency, and we may use it for the communication broadcasting purpose. So thank you very much everyone.